Hi there, today's lesson is on scientific notation, lesson 7-2. The goal here is to be able to use scientific notation to represent very large and very small numbers. So we have sometimes very, very large numbers and very, very small numbers, like this number is very small, it has a decimal point all the way over here on the left. Now, do you notice how there's all these zeros in large and small numbers? Well, writing a number in scientific notation allows us to take all of these zeros here that you see and write them as a power. It holds all of the zeros for us. Because imagine if we were trying to multiply or to divide these numbers, all of these zeros here would make it difficult. I mean, even if we were going to try and type this into our calculator, what if we would forget one of the zeros or accidentally add another one in? And we even have larger numbers than this and smaller numbers than this with more zeros in them. So the goal here is to take a number that's large like this one and write it in a way that we can take all of these zeros and use a power to represent them. Scientific notation, you'll see in your notes, looks like this. But I'm going to first teach it to you, and then we're going to come back to this expression here, and we're going to take a look at what do we notice about the coefficient here, and what do we notice about the exponent, and what does it tell us? Okay, so we'll come back to this one. Now, I'd like you to take a look at what I have here. It says 5 times 10 to the 7th power. Now, you know that 10 to the 7th power is just a shorthand way of writing 10 times 10 times 10 times 10 times 10 times 10 times 10. So imagine if I took 5 times 10 to the 7th power, and I took 5 and multiplied it by 10 this many times, I would get this number right here, 50 million. Now, this right here is scientific notation. It takes this very large number here and all of these zeros right here, it holds that right in this power. So 5 times 10 to the 7th is a way in which we can write this large number. And we're just taking a number 5 and multiplying it by a power of 10. All of the zeros are held right here in that power. So here, 5 times 10 to the 7th power is scientific notation, where the standard regular form of a number would be 50 million. These two are the same thing. But notice how I don't have to have all of those zeros if I write it like this. The power stores all of the zeros for me. Okay? So let's take a look at a few examples here. These are numbers written in scientific notation. I'd like to take these numbers and change them to standard form. What would the number look like? Okay, so let's give this a try. This says 3.54 times 10 to the 5th power. Now, we're not going to use a calculator for this. Now, you know that any time I take a number and multiply it by 10, it moves the decimal point one place to the right. So let's go back up to here. I have 5 times 10 to the 7th power. Now, here's the number 5 with the decimal point right here. Every time I multiply by 10, the decimal point moves to the right. So here, when I multiply by 10, it moves to the right. 10 again, it moves to the right. 10 again, 10 again. Every time I multiply by 10. So here I multiply by 10, 1, 2, 3, 4, 5, 6, 7, and I move the decimal point 1, 2, 3, 4, 5, 6, 7 places to the right. Okay? So right here, this says 3.54 times 10 times 10 times 10 times 10 times 10. Well, that decimal point is going to move to the right. How many times? 5, because we're multiplying it by 10 5 times. So I'm going to go 1, 2, 3, 4, 5. Now, what's going to be in these empty little spaces? Well, zeros, of course. So what do I have? 354, 0, 0, 0. And then I'm going to go backwards, 3 numbers, make a comma, 354,000. So if I took 3.54 times 10 to the 5th power on my calculator, it would be 354,000. Well, let's take a look at this one. 2.08 times, again, 10 times 10 times 10 times 10 times 10 times 10 times 10. Whoa, what a tongue twister there. So imagine multiplying this by 10 7 times. The decimal point is going to move 7 places to the right. It's going to be a large number. 1, 2, 3, 4, 5, 6, 7. Well, in each of these empty spaces would be a 0. So let's write it. 208, and then 1, 2, 3, 4, 5 zeros. Go backward, comma, comma, wow, 20,800,000. Big number. Okay, let's try the last one. 1.6 times 10 times 10. Once, twice, 160. Okay, if you take 1.6 and multiply by 10, it's 16. You multiply by 10 again, 160. Okay, so what I want you to notice here is the first number in every single one of these. Remember how that started? The first number, this was 3.54, this was 2.08, and this was 1.6. Now, this number we can call the coefficient. It's the number that we're multiplying by the power of 10. Now, notice these numbers, 3, 2, and 1. They're all above the number 1, but none of them have 2 decimal places. They're all 9.9 or less. So there's only 1 decimal place to the left of the decimal point. There's only 1 number to the left of the decimal point. That's how you need to write scientific notation. Let's look at these 3. Again, do you see that? 5.45, 2.7, 9.03. Again, there's only 1 number to the left of the decimal point. That's what it needs to look like in scientific notation. Now, what's different about these? This says we're going to take this number and multiply by 10 to the negative 4th power. Well, when you're multiplying by 10, you're moving the decimal point. But if this is a negative exponent, you need to think of this as dividing by 10. This is 5.45 divided by 10, divided by 10, divided by 10, divided by 10. You're dividing it by 10 4 times. Now, this is going to be a very small number. This decimal point is going to move to the left now 4 times. Once, twice, 3, and 4. What's going to go in the empty spaces? Zeros, of course. So decimal point, 0, 0, 0, 5, 4, 5. Again, if we type this into our calculator, 5.45 times 10 to the negative 4th, it would do the same thing. It would, instead of moving the decimal point to the right, it would move it to the left to make it a very small number. Okay? Over here, all of these decimal points move to the right to make it a large number. Here we're moving to the left. So this one, 2.7 times 10 to the negative 6th. Well, really, what's happening here is we're going to be taking 2.7 divided by 10, 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 6 times. So take the decimal point, move it to the left 6 times. 1, 2, 3, 4, 5, 6. Fill in with zeros, and we end up with 0.5027. Again, a very small number, okay? Last one on this side here, 9.03 times 10 to the negative 3rd. So again, 9.03 divided by 10, divided by 10, divided by 10. 1, 2, 3 to the left. 0.00903. Again, a very small number, okay? So not only does the exponent tell us how many places the decimal point is going to move, it also tells us if it moves in the positive direction to the right or in the negative direction to the left. All right, let's do this the other way. Now I'm going to give you a number that's in a number that's in standard form, and we're going to write it in scientific notation. So here we have a standard large number, and I want to write it in scientific notation. So I want to write it as something multiplied by a power. All of these zeros here, I want to hold them in a power, okay? Now remember, if you're looking at this, I want you to find the non-zero numbers right here, 4, 5, 6. The decimal point needs to go somewhere in here where I only have 1 digit to the left. So it's got to be a number that's, a little bigger than 1 point something, but less than 10. So how about right here, 4.56? That would give us one number to the left, right? 4.56. Okay, well, right now the decimal point is here at the end of the number. Think of this as like money, right? If you had all this money, you put two zeros after it, that'd be a lot of money. Okay, so how many places does the decimal point need to move? Let's count. From here, this is where it is in the original number, and we want it to go back here. 1, 2, 3, 4, 5, 6, 7. Okay, so I would write this number as 4.56 times 10 to the, now how many places did it move? 7. Okay, now you have to decide, is this going to be a positive 7 or a negative 7? Well, remember this was a very large number. It's 45,600,000. So this needs to be positive. Imagine if you took 4.56 and multiplied it by 10 times 10 times 10 times 10 times 10, right? Wouldn't that decimal point move to the right and be a large number? Okay. 330. Right now the decimal point's at the end. Where do we need it to be? You guessed it, right here, 3.3. So it needs to move once, twice. So we have 3.3 times 10 to the, how many places did it move? Twice. Now, let's check it. Now, this is a bigger number, isn't it? 330. If I have 3.3 times 10, wouldn't that move it twice to the right to become 330? Yep. We see that this number is bigger than 1, so we have to have a positive exponent. It's bigger. All right, another big number. Decimal points at the end. Where do we want it to be? Look over here. We only want one digit to the left of the decimal point. Do you see right here? 2.025. All right, so we want it to be 2.025. Now, what power? What's our exponent going to be? How many places does the decimal point move? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9. There we go. We have large numbers and we have positive exponents. Okay. Now let's take a look at small numbers. How is this going to be different? Okay, so I've got my decimal point way over here to the left. Where do we want it to be? Look at the non-zero digits, 4, 9. We want it to be 4.9. One digit to the left of the decimal point. So 4.9. Now we need to multiply it by a power of 10. Decimal point would have to move how many places? 1, 2, 3, 4. Now, if I typed this into the calculator, 4.9 times 10 times 10 times 10 times 10, wouldn't you agree that this would be a large number? It's small, so what needs to happen? Exponent needs to be negative. Very good. So now, if I were to go backward and change it back to a standard number, the decimal point would go to the left, which is where we want it to move. Okay, let's try this one. Look at the non-zero digits, 177. Where do we want the decimal point to be? You've got it right here. So 1.77. Now, how many places does it need to move? It's right here. We want to go 1, 2, 3. Again, small number, negative exponent. How about this one? The decimal point's here. Where do we want it to be? You guessed it, right after the 8. So 8 times 10, how many places does it move? 5, negative. All right, we've got it. So, big numbers, positive exponent. Small numbers, negative exponent. All right, now I have a little challenge for you. These numbers, you probably agree that they're not super huge and they're not super small. So how do we write a number like this in scientific notation? I'd like to give you this just to see if I can challenge you. So if you want to pause the video and give it a try, then you can play the video again and check and see if you're right. All right, let's try it. Decimal point's right here. It would have to move to the left one to make it 2. 2 times 10 to the, it moved once, exponent's 1. Now think about this. If I type in 2 times 10 in the calculator, wouldn't that be 20? You got it. Let's try this one. This one's 7. The decimal point is right here. Well, that's where I want it to be. I want one number to the left of the decimal point. So I don't want this decimal point to move. So what power of 10 would I have to multiply it by to keep the 7 the same? You guessed it, 0. 10 to the 0 power is 1, and 1 times 7 is 7. Okay, this one. Again, 6.3, that's what we want it to look like. We want one digit to the left of the decimal point. So again, I don't want the decimal point to move. So I'd have to go 6.3 times 10 to the, you guessed it, 0 exponent. 10 to the 0 is 1, and 6.3 times 1 would give us 6.3. Now this one, there's something wrong with this one. Because this number is less than 1. There isn't a digit to the left of the decimal point. So this is going to have to move one place to the right to become 4. So what power of 10? You guessed it, negative 1. Because imagine if the decimal point's right here, where it should be, and we multiplied it by 10 to the negative first, it would be like dividing by 10, right to the left, which is 0.4, just like this. All right, not bad. Okay, let's try some examples together. I'd like you to take this number and write it correctly in scientific notation. And if you'd like to try these examples, and then perhaps you could just pause the video, and then try them and play the video and correct it, you can do that. It's just examples 1 through 6. I want you just to give a try. So if you'd like to pause it, go ahead. Okay, very large number. Decimal points right here. I want it to be right here, right after the 7, so that this reads 7.892, and now I have a power of 10. How many places does the decimal point move? 9 places. Looks like the answer would be this one. Okay, next one. Decimal points right here. I want it to move in between the 4 and the 5, so it says 4.5. It moved once, twice. But remember, this is a small number, negative exponent. Answer would be this one. Number 3, 204. Right now the decimal point's here. I want it to move to the left 2 places. So 2.04 times 10 to the, well, the number is 204. So to get this to be 204, I want it to move to the right twice. So times 10 times 10 to the second power. Answer's here. Number 4. Very small number. So we know we're going to need a negative exponent. Well, take a look at the numbers here. 2011, I'd want the decimal point to be right after the 2. 2.011. What power of 10? Well, let's count how many places we want the decimal point to move. 1, 2, 3, 4, 5. 5, but again, it's a negative exponent. That's a very small number. So it looks like our answer would be here. Number 5. So we're converting this number back to its original number, 2.63 times 10 to the negative second. So negative 2, decimal point moves 2 places to the left. 0.0263, right here. This says 5.63 times 10 to the 6th. So we want the decimal point to move to the right 6 places. 1, 2, 3, 4, 5, 6. 563 with 4 zeros. Answers here. All right, how did it go? Hopefully great. The last one here. We're asked to figure out which list of these 4 choices has the numbers in order from least to greatest. Well, what you would need to do here is to change each of the numbers in the lists to standard form. It's much easier to compare numbers when they're written in standard form, a standard number, rather than this scientific notation. So I'm going to show you how you would do that. I'm going to tell you that the answer is this one right here. And let's see why. So we want least to greatest, smallest to largest. So I'm going to take this number and change it back to standard form, moving the exponent 3 places to the left. 1, 2, 3, 0.0027. The next one, exponent 3 places to the left. 1, 2, 3, 0.0072. This one, decimal point, 2 places left. 1, 2, 0.027. All right, so this is what you would do for each one of these in order to figure out which one is correctly least to greatest. So comparing here, the first place after the decimal, they're all the same. Now the second place after the decimal, because this is a 2, it's the biggest. Both of these have a 0. So this is the biggest, which so far is good. It's the greatest. It's right here. Now we got to compare these two again. So I'm going to go to third decimal place. This is 2 and this is 7. So when I compare the third decimal place, this is smaller and this is larger. And remember, this one was the biggest no matter what. Okay? So if I look at place value, this is tenths, hundredths, thousands, 10,000s. This is 27 10,000s. This is 72 10,000s, which is bigger. And this is 27 thousandths. So we got least to greatest, just comparing the decimal points. So answer's right here. So again, if you're ever asked to compare 2 numbers in scientific notation, you'll want to change them to standard form, and then you can compare them and decide which one's greater, which one's less. Okay, so let's go back to the scientific notation. You see this right here? I want you to actually flip to the very first page in your notes. Remember the first page was where we had the title, and then right below that, we had this slide. So let's talk about what we've learned. Remember this coefficient here? This coefficient has to be a number that's in between 1 and 9.9. It had to have one number to the left of the decimal point, like 3 point something, or 4 point something, or 1 point something, or 9 point something. It had to have only one digit to the left of the decimal point. So be from 1 to 9.9, okay? It couldn't have two digits and it couldn't be less than 1. All right, then the other thing is the exponent here. Remember, sometimes the exponent is positive and sometimes it's negative. Now, if the exponent is positive, it tells us that it's a big number. Because, and then if the exponent is negative, it tells us that it's a small number. Remember, a positive exponent means we're multiplying by 10 times 10 times 10 times 10. And a negative exponent, that's divide by 10, divide by 10, divide by 10, right? So not only did the exponent tell us if it's a big or small number, but it also tells us the number of places the decimal point moves. Remember, if this was 10 to the 5th power, the decimal point would move 1, 2, 3, 4, 5 places. If it was 10 to the negative 3rd, it would move 1, 2, 3 places to the left. Okay? There we have it. Scientific notation. Have a great day. Bye now.